Okay, welcome to this Friday lecture. So last time we were discussing distributions, okay? So today we're going to focus on distributions of numerical random variables. So let's say, okay, so the topic today is distributions of numerical random variables. So as you remember from last time, so we work on a probability space now, okay? No longer a general measure space, and we have a random variable with values in the extended real line, okay? Whose distribution is nu, okay? So let's say we have nu, a measure on R bar, Borel R bar. So we say nu, X has distribution nu if and only if the probability that X takes values in a measurable subset of R bar is given by nu D. And this is if and only if with the following. So instead of calculating the probability that X takes values in a set, you can calculate the expected value of F applied to X, okay? And in particular, when you take F to be the indicator function of D, this becomes the probability that X takes values in D. So this looks like one step further, but apparently they are even equivalent. So this is the integral of F with respect to nu on the extended real line for every positive measurable F. Okay, so F from R bar to R plus bar, since we said positive, okay? These are equivalent statements, and we sometimes use the notation. So nu dx equals x in dx. So this means you can write f of x as f d nu, or f of x probability x is in dx. This kind of a notation, in particular when you look at nu d, which is the probability that x takes values in d, all you do is to integrate this expression over the set d. So these are all equivalent ways of saying that nu is the distribution of x, okay? Okay. So first of all, you can see this one as the expected value of indicator of d applied to x. And then this is the integral of nu over the set d, which is like indicator d, d nu. Okay. And then, starting with indicators, you can pass to simple positive functions and then to general positive measurable functions. Okay, so from here to here, there needs to be a proof. I guess we either did it or we sketched the proof last time in a more general setting. So now I'm just rewriting things in the probabilistic setting. And from here to here, it's just specialization into indicator functions. Just take f to be indicator of d. Okay? And this characterization is going to be super useful. Today we're going to illustrate why it is so useful. Okay? So the aim of today's lecture is to study some special distributions. Okay? Two special classes of distributions, namely continuous ones and discrete ones. So we're going to start with discrete ones. which are easier, and then pass to the continuous ones. But in general, a random variable doesn't have to be discrete or continuous. There are also random variables which are neither discrete nor continuous, and we're going to see an example of one. Okay, so let's start with the discrete one. So definition. So we say that x is a discrete random variable if there exists a countable set C such that the probability that x takes values in C is 1. We may choose C in such a way that we have x equals x, strictly positive for every x in C. Okay? So once you have a countable set, okay, and for that set, x takes values in this set with probability 1, and maybe for some of the points you have x equals 0. The probability that x takes values, x takes the value x, little x is just 0. You can just delete those points from your countable set, okay? And then you're still left with a countable set satisfying this condition. So you can always assume that in your set C, you only have the atoms of the distribution. Remember the definition of an atom from a homework exercise. So this is nu of x, right? Nu at x. So nu at x is strictly positive, means that x, the singleton x, is an atom of the measure nu. So in other words, let's say you have a random variable taking values in 0, 1, 2, 3, 4, etc., etc. But so this is a countable set, right? 0, 1, 2, 3, etc. But in your set, you can just add -1, -2 as well and assign 0 probability to those. So your distribution may assign 0 probabilities to those, and it is just fine. You just add a set of measures 0, and this is totally fine. So there is an alternative way of writing the definition of being discrete. And for that, I'd like to remind you the definition of the counting measure. So remember the Dirac measure at a fixed point, right? And we generalized Dirac measure to discrete measures, right? If you have a countable set, and at each point on the set, you have a Dirac measure and also some mass, okay, attached to that point, then you have a discrete measure. So discrete random variables indeed have discrete measures. Their distributions are discrete measures, okay? That's why we call them discrete. And indeed, their distributions are absolutely continuous with respect to the counting measure on that set C. What is the counting measure on that set C? Well, just assign mass equals 1 for every point. So just sum of Diracs, okay? Just sum of Diracs. So the counting measure associated with a countable set C is defined as follows. Lambda C is sum of Diracs at the points in C. Okay, so if you have 0, 1, 2, 3, etc., so you just have 1 kilogram to each point. So the counting measure on 0, 1, 2, 3, etc. is the sum of the Dirac measures. So it's not a probability measure, right? So let me put the argument, right? This has to be some set D. So lambda c is a measure on R bar for L R bar. It's one of the examples of discrete measures. Okay, just the masses are equal to 1. Okay, so our characterization is that x is a discrete random variable if and only if its distribution, the distribution we have nu absolutely continuous with respect to the counting measure on C for some countable set C. Well, let's show this. Okay, so we can say it as a lemma, or I don't know, maybe a lemma. So suppose X is discrete. So there is a countable set C such that nu C is equal to 1. And let's show nu is absolutely continuous with respect to lambda C. Okay? So what is the definition of absolute continuity? So the measure, the lambda C measure of a set is 0 implies that the nu measure of that set is also 0. So let D be a measurable set such that lambda C of D is 0. So what does that say? What does that say? So your lambda C is doing what? Is looking at the total mass covered by the set D. If the total mass covered by that set D is just 0, this means what? Your set D is disjoint with C. So C intersection D is just empty. If there were a point in the set, this would have been covered by the counting measure. So then you would just get 1 or 2, just the number of points that you cover. So just lambda C of D equals 0 means you cover no points in your set D. Okay. So C is a subset of, D is a subset of C complement. Therefore, nu D is less than nu C complement. And since this is a probability measure, this is 1 minus nu C, which is 1 minus 1 equals 0. So nu of D is 0. So we conclude nu is absolutely continuous with respect to lambda C. And conversely, if you have, suppose nu is absolutely continuous with respect to lambda C for some countable set C, so note that lambda C of C complement is 0 since lambda C of C is, well, this is just sum of Dirac's, right? C complement X and C. Well, X is part of C, so it's not part of C complement. This is always 0, so we get 0. And by absolute continuity, so nu of C complement must be 0. And since nu is a probability measure, nu of C must be 1. So this shows X is discrete. So this is totally if and only if. So why did we show this? Well, we showed this because we have a famous theorem from last time, which is related to absolute continuity. What is the name of that theorem? The last theorem that we discussed last time. Radon-Nikodym, exactly. So once we have absolute continuity and the sigma finiteness of this measure, or both measures, right? So it is enough to have this being sigma finite, right? So if this is sigma finite, then we are sure that this has a density with respect to lambda c. So note that lambda c is a sigma finite measure. Well, why? Because it is some of those Dirac measures, right? It is some of those Dirac measures, and each Dirac measure is a probability measure. It's a finite measure. So you can decompose your set, the full set omega, in such a way that in your partition, the first set covers this point, the second set covers this point, the third set covers this point, and so on. So you can chop it down into a partition, a measurable, countable partition, right? So by Radon-Nikodym theorem, a density, or we can also say the density, which is unique up to almost everywhere equality, right? A density H, which is the nu with respect to the lambda c, exists. So what does that mean? Well, if you look at the probability that x takes values in D, so this is nu dx over D. Well, what does that say? Just replace d nu with h d lambda. So let's replace it with h d lambda, or lambda dx, okay? Like this. And now this is integration with respect to counting measure. Integration with respect to counting measure. I guess last week when we were talking about examples of integration, so we talked about integration with respect to Dirac measure, integration with respect to a general discrete measure. So we know the answer of this integral from that example. Do you remember what the answer was? So this is integration with respect to counting measure. So all this measure can do when you integrate a function with respect to this is to look at the values of the function at the points of that set and add them up. So it is basically sum of h of x's as long as x is in D and also in C. So you do integration over D, that's why I put D, and you do integration with respect to counting measure, so you only look at the values of the function at the points covered by C. Okay? So when you do integration with respect to the counting measure on the sets 0, 1, 2, 3, etc., all you do is to look at the values of the functions of your function at those points and add them up. That's what you do here. So if you just take D to be a singleton, what do we get? Probability that x equals x is x is in D intersection C. What does that mean? Well, if your singleton x is in C, you get h of x. And if your singleton is not in C, you just get 0. You don't have any terms in your summation. The restriction of H on the set C determines the distribution of X uniquely. Why? Because these are the probabilities that X takes certain fixed values. So if it's a random variable taking values in this set, so if you know the probability that X is equal to 0, if you know the probability that X is equal to 1, X is equal to 2, X is equal to 3, you know the distribution of X, right? Just a discrete setting. Very simple. So what I'm trying to argue is that this function, the restriction of H on the set C, is a very commonly used function in an undergraduate course in probability. And it is called the, anybody remembering this function? Which assigns the probability that it takes a fixed value? Probability, what function? No. Mass function, yeah. So it is called the probability mass function. So even if you don't remember or you don't know what this was, this is it, probability mass function. So in the discrete setting, our distribution is absolutely continuous with respect to the counting measure. Therefore, it has a Radon-Nikodym derivative, and this Radon-Nikodym derivative is the probability mass function. Okay. So in particular, we have expected value of f of x is what? F of x, probability x is equal to x. Of course, this is no longer an integral, just a summation over x's in C. So this is usually given as the definition of expectation in elementary courses. So now this is a consequence, this is a special case of the integration theory that we built last week. So that's an elementary formula for expectation because it's a summation, and you have just the point masses, right, on certain points, right? And all you do is to multiply those probabilities with the values of f, and this is very intuitive definition of expectation, right? So this, you're trying to calculate the expected value of f of x, okay? So of course, x takes this certain fixed value little x with this probability. So you multiply it by the value of the function because you're trying to find the expected value of f of x. So if x takes this value, the value of your function is f of little x. Okay? And you sum it overall, you enumerate overall possibilities for the values of x, capital X. So let's see some examples maybe. Well, I'm just going to discuss the most interesting example, which is Poisson. Okay? For binomial, geometric, etc., I'm not going to talk about them now because I'd like to talk about them at a later stage in a more stochastic process setting, okay? In a Bernoulli trials setting. So we will try to see them in a big picture of Bernoulli trials and so on. Okay? So we're skipping all those binomial, geometric, etc., etc. Okay? So for now, as an example of a discrete random variable, we're going to discuss Poisson. So let's say you have a parameter C, which is strictly positive. So here's the way we abbreviate those distributions. So X is Poisson distributed with parameter C if the probability that X is equal to X is given by e to negative C, C to X over X factorial, for x 0, 1, 2, etc. So this is a short way of writing the following. So x is equal to x is given by this formula if x is one of 0, 1, 2, etc., and it's 0 otherwise. So I provide the probability mass function now, so we know the distribution. We know the distribution. In fact, we can calculate certain quantities about this. First of all, you should make sure the sum of those values, overall x in C, gives you 1. So just check sum of those probabilities, 0 to infinity, gives you 1. This should be the case in the probabilistic setting because at the end of the day, nu is a probability measure. Nu is a probability measure. So if you take D to be just 0, 1, 2, 3, etc., you should get 1. You should get 1. Well, this is, we can just see it, right? The e to negative c is just a constant, so x0 to infinity, c to x over x factorial is even the definition of e to c, so we get 1. You can take it as the definition of the exponential function, so this is just 1. And what you can also check is that the expected value of x, which is x times e to negative c, c to x, x factorial, 0 to infinity, gives you c. And expected value of x squared is x squared e to negative c, c to x, x factorial, is c squared plus c, so that the variance of x is expected value of x squared minus the square of the expected value. So c squared plus c minus c squared gives you c. So the expected value and the variance are equal, and they are equal to the parameter of the distribution, c. So if you don't remember how to do such things, how to calculate such things, for instance, we can look at the first one, if you like. Well, there is x here and x factorial here, so this should become an x minus 1 factorial. And we can also start the summation from 1, because when x is equal to 0, we just have 0. So let's start it from 1, and let's get rid of one of the x's. Okay? Now you can write it as follows. I have x minus 1 here and x here, so let's write it as this. C to x minus 1 times c. Okay, so this c is a constant, and I can reindex the summation from 0 to infinity again. C to x, x factorial, which should give me 1, because it's the sum of those probabilities. So we just check that this is 1. So the answer is C. And you can do a similar thing for x squared. Perhaps you need a few more steps. Anyway, so these are some little tricks, calculus type tricks, right? Okay, so the discrete case is nice and not very difficult. So the other corner case is the completely continuous version. So this is like purely discrete, right? You have just points, And now we're going to have a continuum of values. So let's define continuous random variables. So let's assume x is real valued, okay? Suppose x is real valued. We say that x is a continuous random variable if its distribution is absolutely continuous with respect to the Lebesgue measure. So let me just remind you that where nu is the distribution of x. So I did not define it in a different way, and we're not going to prove that different way is equivalent to some absolute continuity. We directly define it using absolute continuity. And there is a reason for that. Maybe before we talk about the details, let's put it as a remark, okay? Remark. So if, or let's write it this way. So x is a continuous random variable implies that the distribution is diffuse. This means it has no atoms. In other words, nu of x is 0 for all x. It has no atoms. Okay? So how can we check this? Well, note that the Lebesgue measure of x is 0 for all x. And since nu is absolutely continuous with respect to the Lebesgue measure, so if a set has Lebesgue measure 0, it must have the distribution measure equals 0 for all x. That's the proof. Okay? But the converse, so the converse fails to hold in general. So if you look at this definition of discrete random variable, or let me wait a moment, okay? Okay, so if you look at the definition of the discrete case, it is the purely atomic case. You have a countable set, okay, over which the random variable takes values with probability 1. So it is purely atomic, okay? You only have points that are atoms of the distribution. You only have points with this property, that x takes this value with strictly positive probability, and on the rest you have 0 probability. So your distribution is concentrated on a discrete set of points, a countable set of points. So that's the purely atomic case. And if you think about the other extreme, it is the diffuse case, meaning that the distribution has no atoms. Okay? So if the distribution has no atoms, then we cannot conclude that x is a continuous random variable. But if x is a continuous random variable, nu is this diffuse. Okay? And this nu is diffuse if and only if the cumulative distribution function f is continuous. So recall f of x is defined as the probability that x is less than x. So this function is in general right continuous and increasing, and now it's continuous and increasing. It has no jump points. Okay? So this is if and only if with being diffuse. But it is not if and only if with being a continuous random variable. Okay? Apparently there are random variables that are not continuous random variables, but their distributions are still diffuse. Okay? So that is not a one-to-one characterization. it is different from the discrete case, right? In the discrete case, you have absolute continuity with respect to some counting measure is if and only if it being discrete. Here, being a continuous random variable implies that the distribution has no atoms, or in other words, the cumulative distribution function is continuous function, but not the other way around, okay? So just as a side note, a random variable whose distribution is diffuse, but not a continuous random variable is called singular continuous, okay? So this is something related with some details about the proof of Radon-Nikodym theorem, which we skipped. So that's why we don't talk about such little details, okay? But the main idea is that there are continuous ones, there are discrete ones, and there are other ones, okay? And among the other ones, there are random variables whose distributions are diffuse. Still, they are not continuous random variables. That's a weird point, but we're not going to explain the mathematical details of that point. Okay, so now let's talk about nice examples. Well, before the examples, maybe we should just talk a little bit more about this definition, okay? So we have new absolutely continuous with respect to the Lebesgue measure. What does that say? What does that imply? So by Radon-Nikodym theorem, there is a density. Well, first of all, note that Lebesgue measure is sigma finite. So by Radon-Nikodym theorem, a density H d nu d Lebesgue exists. So if you look at the probability that x takes values in d, this is the integral of nu dx over d. So this is the integral of hx Lebesgue dx over d. In fact, if you have the probability that x is between a and b, what is that? It is h of x Lebesgue dx over a to b. What does this imply? What is the result of this integral? So it is integral with respect to Lebesgue measure. What was the connection to earlier calculus? So Lebesgue measure is just length, right? Therefore, we expect that the integral with respect to this measure will coincide with what integral? Which integral? Riemann integral, right? So this is a to b. So now I'm writing a to b, not like over a set, but I'm using the calculus notation. So that's the Riemann integral dx, as long as h is Riemann integrable, etc. Yes? Yeah.
But for this one, we need some assumptions on h.
Exactly. Yeah. Yeah. As long as, so let's write, as long as h is Riemann integrable. So let's think Riemann integrable. But what we do is to kind of abuse this notation a bit and just put dx, even if it is not the Riemann integral. So when you see dx, it doesn't have to be the Riemann integral. It doesn't have to be a Riemann integrable function. We don't worry about Riemann integrability too much. So whenever we have Lebesgue dx, we just abbreviate this as dx. And in particular, we have expected value of f of x is given as f of x h of x dx over the real line. Okay? And again, this is an old formula. So in the continuous case, this is given as the definition of expectation. Okay? So let me show you the other formula. For the discrete case, the formula was this, right? So f of x times the probability that x takes this fixed value, little x. In the continuous case, we have f of x times the density. Okay? So indeed, this h is called the probability density function. Of x. So let's look at some nice examples. For some of you, they're going to be just the old examples. And for some of you, maybe this is totally new. So we say, let's say we have a and b, okay? Just real numbers. So we say x has the uniform distribution over the interval a to b if its probability density function or its distribution is given as follows. 1 over b minus a dx for x between a and b. And this totally means the following. X is in dx. 1 over b minus a, indicator ab of x, dx. Okay? In other words, if you look at the probability, let's say a is 0 and b is 1, and you look at the probability that x is between minus 5 and 0.5, it is really the probability that a is between 0 and 0.5. So below a and above b are not interesting for us. It takes the values over those regions with probability 0. So all this is trying to say is that the probability density function is a constant over the interval a to b. And we just make it 1 over b minus a because we want this area to be 1, right? So that this makes a probability distribution. Again, you can worry about things like, oh, should I include this point here, or should it be left continuous instead? Why do we include those points A and B? The answer is we don't worry about such things, because if you have the other picture where you exclude A and exclude B, like this, this is also a version of the Radon-Nikodym derivative. So when you do calculations with this versus with this, you will get the same results. Because at points A and B, so the points A and B form a null set of the Lebesgue measure. So it cannot change the result. So all calculations like probabilities, expectations, and so on are integrals with respect to the Lebesgue measure. Therefore, if you have a set of measures 0, Lebesgue measure 0, it cannot change the end result. So both are versions of the new Lebesgue. And if you don't remember what we mean by a version, just look at the statement of the Radon-Nikodym theorem from last time. So we said the Radon-Nikodym derivative is unique up to almost everywhere in equality, and almost everywhere is with respect to that dominating measure, this Lebesgue measure in this case.